Welcome to College Algebra. We're working on Chapter 4, Section 2, and dealing with exponential functions. Okay, an exponential function is any function that has a variable or the letter as the exponent. Examples of this are f of x is equal to 3x, or you have a number as the base and your exponent is the x. So your variable is in the power. Okay, f of x is equal to 2 to the x minus 3. X minus 3 is your power. So that's an exponential function because the exponent is the x part. And then f of x is 5 to the negative x, or your negative x is your power. Now, we can find graphs of exponential functions by plotting points, just like we have in the past. So as we have 3 to the x, if you plug in 0, you will get 3 to the 0 power, which is 1. And so we have the point 0 is our x value, 1 is our y value, so it's 0, 1. If you plug in 1, you get 3 to the first, which is 3, and you have the point 1, 3. 2, when you plug it in, is 3 to the second, which is 9. So you have the point 2, 9. And again, 2 is your x value, 9 is your y value. Okay, if you plot those on a graph, over 1 up 0, over 0 up 1, 1, 3, and 2, 9. When you connect the dots, you get a graph that looks like this. It never reaches 0 horizontal. It flattens out. It always goes through the point 0, 1, because when you plug in 0, you always get 1, as long as it's just an x power. And so anytime you have a base larger than the number 1, it's going to look like this. Now when we look at the function 1/2 to the x, we can do the same thing. When you plug in 0, you get 1/2 to the 0 power. And 1/2 to the 0 power is 1. So you have the point 0, 1. When you plug in 1, you get 1/2 to the first, which is 1/2. So you have 1, 1/2 is our point. Plug in 2, you get 1/2 squared, which is 1/4. So you have the point 2, 1/4. When we plot these points, we get the same starting point, 0, 1. Then you get 1 goes up 1/2, 2 goes up 1/4, and it keeps getting smaller and smaller, so it flattens out. So this particular curve starts way up high and goes down. Again, it never reaches 0, and it always goes to the point 0, 1. Now, anytime you have a fraction less than 1, that's what the graph is going to look like. Okay, all the transformations that we've done previously still apply. If you add a, it moves up. If you subtract, it moves down. If you add a next to x in parentheses, it moves left, because it's the opposite of plus. You think plus is right, but plus is left. Minus, you think is left, but it really is right. A minus in front of your function. That's a negative, and it changes your functional value, your y value, which means your reflection across the x-axis. And if you put a negative x, you're changing the x value, you're jumping in across the y-axis. So that's all your transformations. Now when you're sketching, suppose you have 3 to the x plus 2. We follow the same things as we did before. You're going to take the 3 to the x graph and plus 2, which means you're going to move it up 2 units. So here's our 3 to the x graph, just sketched. Again, it went through the point 0, 1. We're going to move it up 2 units. So I just count up 2 and sketch it. 2 to the negative, or x minus 3. You're going to take your 2 to the x, which looks just like 3 to the x. You're going to subtract 3, which means you're going to move it to the right 3. So count 1, 2, 3. This point just moves right 3. Now suppose you have 5 to the negative x, or a negative power just flips over your fraction, which makes it 1/5 to the positive x. Now we have a fraction, so we take our 5 to the x power. When you flip it over, the negative just brings it down that way, and so 5 to the negative x just flips it around. And in that particular case, again, we backwards. If you flip this across the y-axis, because it's a negative right in front of x, these values jump across over here, these values jump over there, and you have what's there. Okay, if you're going to solve an equation, suppose you have 25 equals 5 to the x plus 2. What you need is this 25 to be a base with a power. So we make this 25 into 5 squared and 5 to the x plus 2. So we just change our number 25 to a 5 squared. Then we have the bases the same, which means our powers, our 2 and our x plus 2, have to be the same. Then when you solve that by subtracting 2, you get x is equal to 0. Okay, suppose you have something like 4 over 81 is equal to 9 over 2 to the 3x power. Again, we need our bases to be the same. So if you change 4 to 2 squared and 81 to 9 squared, you have 2 ninths squared, because 4 is 2 squared and 81 is 9 squared. So now we have 2 ninths squared and 9 halves to the 3x. Well, they're not quite the same, so we have to flip one of them over. Now I've chosen to flip the one on the left, so it becomes 9 halves with a negative power. Anytime you flip things over, it was 2 ninths, I flipped it, making it 9 halves, negative power. Now the bases match, so negative 2 has to equal 3x. And when you divide by 2, x has to equal negative 2/3. Alright, suppose you want to reverse the process. Find an equation, f of x is equal to some base to the x power, and I give you a 0.29. 2 is my x value, so it goes up here as x. And 9 is my y value, so it goes as my f of x. So 9 is equal to a squared. Take the square root, and a has to be 3. So our original function is now f of x is equal to 3 to the x. Okay, a couple of applications. There's a compound interest formula. A is equal to P, open parentheses, 1 plus R divided by N, close parentheses, NT power, where A, big A, is the amount that you're going to end up with, like after 10 years, 15 years, whatever. P is the principal, that's the amount you start with. This R right here is your interest rate, and it must be a decimal. N is the number of times they're going to pay you every year. For instance, annual is once a year, monthly is 12 times a year, weekly is 52 times a year, and daily is 365 times a year. And then T in our equation is the number of years that they're going to pay us. Okay, suppose you want to find out how much you're going to have if you invest $10,000, 8% for 40 years, compounded monthly. So we put our numbers in. We're going to invest, that's what we're starting with, $10,000. Our interest rate is 8%, 40 years. We put those numbers in, 10,000, 1 plus 8% is 0.08. Monthly is 12. And then our power up here, 12 times 40. And if you're using a graphing calculator, you just need to type 10,000, open, 1 plus 0.08 divided by 12, close. Then you put a caret for the power, and you must open parentheses. If you do not open parentheses up here, you're going to get the answer incorrect because the calculator doesn't know you have a power. So you put a caret for a power, open 12 times 40, and close. And I believe you get 242,733.8554. And on the test, I usually truncate that and just count the cents. Okay, compound continuous interest. Now some banks, to make it sound better, they have what's called continuous, and that's more often than once a year. That's more often than monthly, weekly, daily, every minute. It's continuously. It never stops compounding. And the formula is A equals PE to the RT. A is the amount you end with. P is the principal that you start with. E is a number on your calculator, 2.71828. And there's an E key on your calculator. I believe it is well, most calculators it's going to be in yellow. It's a second function right above the LN, left side about 2 up from the bottom. Again, R is your interest rate as a decimal, and T is the number of years. Okay, suppose we want to find out how much you're going to have if you invest $10,000, 8%, 40 years, compounded continuously. Should be similar to what we had earlier. So if you put in the number A, that's what you're looking for. P is the principal, is 10,000. E is just the number, so you just leave it in there. And then The power is 0.08 times 40. And when you type in your calculator 10,000, then to get the E, you push second L in. And then 0.08 times 40, you should get 245,325.302. So it's close to what we had earlier. It just should be slightly more. In fact, if you look back, it was 342. Now it's 345. You're about $2,000 more than you were before. Okay, a couple more examples. Suppose you want to find out how much you're going to have if you put in $6,000, 12%, 20 years, compounded every week. Again, if you look back at the formula for compound interest, 6,000 is what you start with. 1 plus 12% is 0.12. Weekly, there are 52 weeks in a year. Then 52 times 20. It's really important. 6,000, open parentheses, 1 plus 0.12, divided by 52, close parentheses. Then you type a caret for a power, open 52 times 20. I come up with 65,596, or 956 if I did that right. And then the final problem, we're going to reverse things. What annual rate, so we're going to look for R, will make $5,000 grow to $9,000 in 5 years? So we put in the numbers. It's 5 years, annual, so we're not compounding continuously, so you put the numbers into the compound interest. 9,000 is what you want to end up with. 5,000 of what you're starting with. 1 plus our rate divided by 1, and our power is 1 times 5. Okay, the first thing we need to do if we're solving for R is move this 5,000 over. So 9,000 divided by 5,000 should be 1.8. Then you get 1 plus R to the 5th power. Then we need to move this 5th power by taking a 5th root, which is a 1/5 power. If you type that in your calculator, you should get 13.47. When you subtract 1, your final answer is 12.47. So that's exponential equations and some applications.